Hello again.
Hi, I'm Rohith. I work with Ericsson Cloud SDN Switch team.
Okay, and our talk now is about the experiences that we have gathered in troubleshooting data plane issues with OVS DPDK, to be precise again, in our NFVI deployments in the past year, the difficulties we've been facing, the classes of problems, and the things that we have been doing and are still doing in order to improve the capabilities of OVS DPDK to help troubleshooting these things. We have two classes of problems. I will talk about the first one. It's real-time packet drop at OVS boundaries. And then Rohith will talk about the packet drop inside the OVS data path and pipeline. So let me start with the real-time packet drop OVS boundaries. What do I mean with this? This is a pretty full slide. Focus on the picture on the right-hand side. So we have OVS DPDK with the PMDs pulling packets from queues. And this is high performant. We are running a lot of traffic through it. 4 million packets per second with a single PMD is a typical figure, really. And you have a number of queues in here. We have the queues RX and TX on the NIC. We have RX and TX queues on the vhost user port virt.io towards the VM. And in many applications, especially DPDK applications, there are also internal queues where packets are being buffered temporarily while the traffic is running. And such systems are typically run at a fairly high utilization level because this is end-user flows, several hundred thousands in parallel. We have a large statistical sample. Traffic is pretty even. So nobody wants to really dimension the system to leave 50% spare capacity. And it's actually possible to do so. But these queues are a weak factor. And in particular, the queue in QEMU, the virt.io queue that is limited, hard-coded in QEMU versions up to 2.9 to 256 descriptors. And the way these descriptors are used depends on the device and the drivers and so on, but typically every packet consumes 2 descriptors. And that means we have 128 packet queues here. And with 4 million packets per second, you can see that it takes roughly 32 microseconds for this queue to run full, which makes the whole system extremely vulnerable to real-time disturbances. Any real-time disturbances in the order of 50 microseconds can cause queue overruns and then packet drops. And people have been fighting with this for a long time. Many of these kind of disturbances are well known, are documented in a lot of tuning cookbooks. But we are surprised that it's a never-ending story. Every time you think you have found and fixed all of them, new ones are turning up. And it's really difficult to troubleshoot these problems, and I'll tell you why. Now, first of all, these drops only really happen at maximum load levels. If you are not running at maximum load levels, the queues kind of hide your real-time disturbances. When packet drop happens, it's typically only visible in end-to-end, and the troubleshooter has incomplete data because the most likely place where packets are being dropped is these virt.io queues, and especially in the transmit direction from the VM into OVS. And obviously, OVS has no knowledge of these packets being dropped. If you ever check the vhost user account, there's always a 0 RX packet drop. And that is because OVS is not aware and cannot be aware that the tenant is dropping packets because the queue is full. So in order to find out that packets are being lost there, you really need to have access to the VM, and you need to have access to the troubleshooting commands to read those packet drop counters. So it's really difficult. Then these packet drops occur infrequently, right? Everything between 10 seconds and 10 minutes interval. In the best case, they are periodic. Then you have a better chance to track them down, but normally they are not, or often they are not. Then these bursts of drop packets are extremely short, like typically well below 1 millisecond. Our existing tools that we have, port status counters, we call them repeatedly with a sleep in between, like 1 second granularity. You can imagine that it's impossible to really find out when these packet drops happen, and if there are multiple of them in a second or not, and so on. And it's extremely hard to correlate drop events with other events in the system due to this lack of timing. And then these drops are statistically insignificant, right? You have averaged over time maybe 100 ppm drop. This is far too much for benchmarking and also for application requirements. But the impact on anything but packet drop counters is negligible. So what did we do? We developed a tool internally for our OVS DPDK-based vSwitch in the solution, and we used it to troubleshoot all these problems in-house. It consists of 4 things. First of all, we collect and capture PMD metrics in every iteration of the PMD. We feed this into histograms for these metrics so that we get a detailed statistical distribution of these metrics that we can look at. Then we record all the iteration metrics in a circular buffer of a length 1,000 iterations. I'll come back to that later. And we also compute averaged or summary values over a millisecond and store these millisecond values in a circular history covering 1 second total time. And that is, can be done very efficiently. So we have measured it's less than 1% performance impact, and which means that you can have that always active. We had a conditional build option for that initially, and then said that it's not worth it. It's much more important to have it available always as an online tool without having to deploy a debug binary. Now, let me speed up a bit. So there's a new command, dpi netdev PMD perf show, with a couple of options. And when you run it, you can get a large printout, much larger than the one that is shown you. And I'll show you the different segments of that in the next slides. It starts with the PMD Performance Summary. The data in it is very similar to what you get with the existing PMD stats show. It contains a few additional things, and it's hopefully much more easy for human readers to comprehend and to interpret. I'm not going to go into that in more detail. The interesting parts are the histograms. So we have a couple of metrics that we record per iteration. And for each of them, you have a histogram. Every histogram is like this big orange box there. So we have a couple of bins, 32 bins, with the upper bound of the bin and the number of hits in the histogram. And we have histograms for the cycles per iteration, for the packets processed per iteration, for the cycles per packet, for the packets per RX batch that were polled, for the maximum vhost user queue length that was observed while polling vhost user ports, and that is important because that is our only clue inside OVS to see are vhost user queues running full. So this is the only way we can infer that there's a risk of packets being dropped there. Then we also have 2 metrics for upcalls. One of the number of upcalls that happened in an iteration and the number of cycles per upcall in that iteration. And below you have the average values for these metrics also. So this gives you a very good overview of the way the PMD performs. On top of that, you have these circular histories that you can dump. This is the iteration metrics history, the same metrics, but for every iteration. And we have a similar history for the millisecond averages or totals. So they can be dumped at any time. And it gives you a pretty good overview of what had happened. Now, you still need to solve the question on when such a drop burst happens, just takes less than a millisecond, happens at any time. How do we capture it still? What we have implemented on top is a supervision. So every PMD supervises the metrics that it collects every iteration, and if it finds a suspicious iteration, and you can configure what suspicious means, then it actually dumps the context, so the history of the iterations around that event into the vSwitch daemon log. And you can basically dump up to 1,000 iterations, and that is 2 to 5 millisecond history around the event into the vSwitch daemon log. And that has proven extremely helpful to understand what is going on in these events. Because you can let it run, and you can do an offline analysis of what has happened. You find out exactly when these drops happen. You find out the periodicity. You can have timestamps you can correlate with something else. And you can get this data around it. So we have been using that internally in our product for several months in system test, really heavy duty. It's also out in the production version in Ericsson NFVI deployment since May. So we believe this is pretty mature and robust. And there is an upstream version of that which has been refined a bit, and it's submitted, and it's waiting for reviews and tests. And we really would appreciate feedback here to make it into the code. I have a couple of cases that you can look at that we solved using these tools. I don't have enough time to go through it. I would like to hand over to Rohith now to talk about the second class of the problem and how we're addressing that. Thank you.
Let's look at the second category of problems, that is packet drops in OVS pipeline data paths. This slide shows gives an overview of the OVS DPDK architecture. Now let's look at the various drop scenarios in the OVS. So packet drops could happen because of the errors in the OVS proto layer. This generally manifests as drop action to be executed in the data path. Drop action also executed because of explicit drop action configured as part of the OpenFlow pipeline as well. Also, we have drops happening at the interface level, and any errors or exception during the data path processing also result in packet drops. So now let's look at how we can monitor these drops. So today we can monitor only the drops at the interface level. So one would run the interface stats command to monitor the drops at the interface level, but we don't have any other mechanisms to monitor the other drops. So what about the drops happening by the drop action? So the drops which are happening because of the translate errors in the OVS proto layer are not accounted anywhere. And some drops which are dropped by the drop action, which are explicitly configured through the OpenFlow pipeline, are reported as part of the OpenFlow stats, but that can be interpreted only by the controller. And any errors or exception during the data path processing will result in the silent drops. And if you are lucky and if you turn on the logs at the debug level, you might get some information about these errors. So let's look at what troubleshooter really need. So first and foremost, we want to account each and every packet drops happening in the OVS so that one could confirm at least the packet drop is happening or not. And second, if you if you know the packet drop is happening, then the next thing is I would like to get a quick view of why this packet drop is happening. This can be done by categorizing the drops by their drop reason, or could be by the drop location, or could be the drop type. And this consolidated and categorized drop information should be available easily through a single interface. It shouldn't be that the troubleshooters has to run multiple commands and get the outputs of those commands to correlate this data. And it's often will be the case that just by knowing the drop reason, we will not be able to root cause the problem. So we might, in certain error conditions, we might need additional information. The additional information could be that we want to look at the packet data at that point of time, or packet metadata, or it could be as simple as some extra logging is required to further troubleshoot this problem. It will be good if you have a feature which will, on the need basis, provide this extra information. And then whatever the enhancements we are going to do, it should not impact on the real-time performance. Now let's look at what we are doing to improve this OVS packet drop infrastructure. First, we are enhancing the drop action handling. So currently, any errors in the OVS proto layer will result in installing the drop action. So in addition to that, we are also storing the drop reason, like basically the reason for installing the drop action. So we use this drop reason later to classify the packets, classify the drops because of the drop action. So here I have shown very high level of classification. In the next slides, I will have a detailed classification done for the packet drops. Again, any drops happening during the any stage of the data path processing are now accounted and classified. so that we can get an overview of where the packet drops are happening. So this is how the packet drop classification is being done. So the RX drops account for all the packet drops happening till the initiation of the data path processing, and any drops happening during the data path are classified as data path processing drops, and drops happening after the data path processing are classified as TX drops. The categories under the data path processing are further classified. Let's look at them. So the drop action classification is like this. So any drop action installed as part of the OpenFlow pipeline processing or the errors generated during processing the OpenFlow pipeline, for example, table lookup miss or the group ID, non-existent group will be classified under OpenFlow drops. And any drops happening because of the translation error or comes under translation error drops. And any drops happening because of the invalid port state or the invalid config will come under port state drops. And the last category is the contract drops. This is still a pending work and need further investigation. The idea here is that any drops happening as part of the connection tracking processing should be classified under this bucket. And other data path processing drops are upcall drops. So this account for any drops happening while initiating the upcall or the explicit drops happening because of the error returned as part of the upcall processing. And data path exception drops account for all the errors and exception happening while during the data path processing. This is how the new drop statistics CLI looks. The idea here is to get the consolidated and categorized and detailed drop statistics, so that by just running this command, one would get confirm whether drops is happening, and if drops are happening, what could be the possible reasons for that. In addition to that, because we could classify the drops at so granular level, we could add a new infrastructure called dynamic debug infrastructure. With this infrastructure, what we can do is at any drop error or counter level, we can dynamically turn on extra information retrieval feature. This feature could be like we can get a packet dump or packet metadata, or if you want to re-inject for the upcall processing, or it could be that as simple as getting a debug logs, extra debug logs for any counter, we can dynamically turn on and turn off at any drop counter level. For example, let's say for example, for a recirculation errors, you want to turn on the logging. So you can just do the logging, turn on the logging for the recirculation errors. Or in addition to that, let's say if you want to get a packet dump for the recirculation error, we can enable that, and you can turn it off or turn it on anytime you want. The next couple of slides gives an example how we use this tool to troubleshoot some of the problems, and also taken an previous instance where these tools were not available and how difficult it was to troubleshoot the problem. In the interest of the time, I will skip these slides, but offline we can catch up for the discussion. So what are the next steps? So we really want to extend this infrastructure so that we can also troubleshoot the packet misforwarding as well. So this is a very early stage, and some of the thoughts we are having is, for this we would like to have a new action called trace action. So any packets or flow hitting a entry which is associated with the trace action, we can track all the data path processing for that. In addition to that, we can blend with dynamic debug infra so that to get extra information like packet data or logging or any other features we want to add on. And also would like to orchestrate this the trace action from the OvS proto layer so that we can associate the trace action with at any stage of the OpenFlow pipeline. And as I said, this is like still a very early stage, and any further suggestion inputs are welcome on this. To summarize, troubleshooting the packet drop in live NFI system under load is really hard, and we have introduced two class of troubleshooting tools here. The first class of tools will give you the real-time PMD performance metrics and supervision, with which one can hunt down these sporadic drops at OVS boundaries, and this is already ready and ready for upstreaming, and we would like you to use this tool and give your feedback. And the second set of tools will give you information about enhanced packet drop statistics as well as dynamic debug handlers. And this is really a work in progress, and this will help in efficiently identify and debug all type of packet drops inside the OVS. And also we would like to mention that these tools are aimed at having a minimal impact on the performance, and we would welcome any suggestion and collaboration for improving these tools. Thank you.
All right, we have some time for questions. There's some microphones in the back, and I can also run them to people who aren't near one if you like.
Hi, I'm a big fan of monitoring and debugging, so I'm big +1 for this classification. And my question is, are you thinking about only logging from the monitoring perspective? Do you thinking about time series monitoring or those kind of additional better monitoring with the lots of data generated by this?
I didn't get the question. Can you repeat?
Yeah, it was difficult to understand acoustically.
So my question was, do you thinking about time series logging or time series monitoring instead of just generating logs in the log file?
Are you thinking about time series logging or monitoring?
Time series logging. No, I mean, right now the supervision is looking at individual iterations, so not at any evolution over time.
Okay. Thank you.
Boy, with all those lists of ways things can go wrong, it makes me wonder how things can ever go right. I believe we have do we have a question over here on the right? Oh, no, that's not that. All right, please go ahead.
Hi there. So I've recently been exploring the OVS Netlink Datapath, and I was looking for metrics very similar to this. So when these get upstreamed, will these be available via the Netlink Datapath or elsewhere? Like, what can I do to retrieve these metrics without necessarily shelling out to the tool, the appctl tool?
Yeah, the work that we've been doing is explicitly targeting the DPDK data path. As far as I know, there is no similar implementation available for the kernel data path. I don't think it could not be done, but I'm not a Linux kernel developer, so I'm very badly qualified to judging whether that is realistic or not.
Sure. Thank you.
Mm-hmm.
Yeah, hi, I have just a quick question. So a lot of time when we have to debug issues, like when there's a lot of traffic going on in the switch, but there's only 1 or 2 connections that are like the user really care about, and those get dropped occasionally. And doing packet capture would be like too much data when you do packet capture. So have you looked at with the metadata, can you filter based on certain tuples or things like that as well, in addition to just capturing all packets going through the switch?
Yeah, actually, that's one of the things. Like, so we are not covered here is that how we can, let's say, narrow down the capturing mechanism. Like, for example, we can have a inbuilt rate limiting as well, and also we can specify at what rate you want to capture the packets, and whether any specific flows you want to capture, we can add that as part of the dynamic debug infra. Yeah.
Do you know how much performance impact that adds to the, what's the overhead that is?
We have not measured the performance as of now in that, yeah.
We have time for one more question.
So you just said it has some impact of performance. So can we disable or enable this in the runtime?
The question was if this impacts the runtime performance, or?
I mean, if we can disable this in the runtime, it cannot impact the performance, right? If we need to debug some problem,
okay.
We can enable this in the runtime.
Well, the current upstream patch is kind of it's unconditional. So you have it, and it will impact the performance by this less than 1%. You cannot disable it. But I mean, this is up for discussion in the OVS mailing list. So if people believe that there's a high value of making this build time option, then of course we need to discuss it. But I personally don't believe it's worth it. It's much better to have it on always. And we gain the performance through other optimizations, again.
All right, let's thank our speakers.
Okay.